output 跟 input 的这个大小的关系 ，phase 是 delay 的关系，哈，就是你的 output 跟 input 可能会稍微 delay 一段时间的关系，哈。那我们昨天也讲到说，一个 pole 呢，它事实上会给你一个负90度的 delay， 一个 zero 会给你正90度的 delay， 这样子啊，不是 delay 啊，就是正90度，一个是负90度，哈，的 phase shift。那事实上呢，一个 pole 呢，它是可以给你到负90度，好，但是呢，真正达到负90是在大概无限大的频率的地方 ，OK， 所以虽然它可以到负90，事实上在这个你真正会操作的频率是会接近负90，但是不会真的到哈。如果2个 pole 的话呢，是会接近负180度，3个 pole 呢会接近负270度这样子哈。所以呢，当你的系统里面有3个 pole 的话，你才有可能在某个你会操作到的频率呢，达到负180度的 phase shift。OK， 那负180度的 phase shift 呢，事实上它在讲一件事情，就是原本你的这个信号可能是一个旋波，在 phase shift 负180度的时候，它基本上就会变成刚好反过来的一个旋波。OK， 那刚好反过来的旋波会造成什么状况呢？刚好反过来的旋波呢，事实上会造成一个positive feedback 的状况哈。那简单来讲，就用这张图，我原本呢，这个本来是要做 negative feedback 的，但是因为刚刚好哈，在负180度的那个 frequency omega 1， 那它反过来了，反过来了以后呢，它又送回来做 negative feedback。结果它减掉它的反过来，反而变成一个更大的讯号哈，所以它就变成了 positive feedback。这个是造成震荡的一个状况。那造成震荡的这个 criteria 呢，就是这个 loop gain， 我们现在叫做 loop transmission。这个 loop transmission 等于负1的那个频率哈。那它要等于负1，就是2个，一个是它的振幅等于1，一个是它的 phase shift 等于负180度。这2个东西同时成立的时候，就是它的 minimum 的 criteria 哈，就是最小要让它发生震荡的状况。那当然就是说，如果你的 phase shift 等于负180度，然后你的振幅大于1，那它更是会震荡哈，因为它的振幅大于1的意思就是这个地方更大，它是反过来，但是这里更大这样子哈。那减回来的话，这个会变成更大。OK， 所以 phase shift 是负180度，但是振幅等于1，基本上是它的 minimum 的 criteria 哈，震荡的 criteria。OK， 那在这种状况下呢，这里就是一个例子哈。那我在 phase shift 负180度的时候呢，这个 omega 1的频率，事实上它的振幅好，这个 loop transmission 的 magnitude 大于1，好，所以这样就会造成震荡。好，那我们昨天也看到。所以呢，基本上你的电路能不能稳定的一个条件呢，就是你的 gain crossover 好，必须要早于这个 phase crossover。gain crossover 呢，就是你的 loop transmission 的绝对值等于1的时候，好的那个 frequency 叫做 gain crossover。phase crossover 呢，就是你的这个那个 phase plot 呢等于负180度的那个 frequency。叫做 phase crossover。在这个图的例子上呢 ，gain crossover 等于 omega 1， 那个 phase crossover 等于 omega 2。好，那 omega 1先发生了，就表示呢，真正在负180度的时候呢，你的magnitude of loop transmission smaller than 1， 好，所以它不会震荡，它就会 stable。好，那大概就是这样。我们昨天讲到这边，今天我们从这个地方开始给大家讲哈。Okay, so we talk about the stability is that your gain crossover should happen before your phase crossover. So let's look at several conditions. The first one, this one, your gain crossover is exactly equal to phase crossover. Okay, it's the same frequency. Okay, what happens when your gain crossover is equal to your phase crossover? It means that it actually meets the criteria for oscillation, right? Because this is minus 180 degree, and this is this means that your magnitude of the loop transmission is equal to 1. Okay, so basically this is -1. So when this happens, it satisfies the criteria for the system to oscillate. Okay, so you will see if we have a step function in the at the input of this system, the output will oscillate like this. Okay, so this will oscillate. If your gain crossover is slightly before the phase crossover like this, okay? If your gain crossover is slightly before the phase crossover, you are going to see something like this. Well, this is a step function, and basically your output tends to be stable. However, you will see some oscillation. Okay, so this is when your gain crossover is slightly earlier than your phase crossover. It's easy to, you can still imagine because at the phase crossover, if your input is a sinusoidal wave, your output is also an inverted sinusoidal wave, but the amplitude is a little less than the input. Okay, so basically it kind of oscillates, but eventually it will become stable like this. Okay， 所以呢，在这个地方你看到的是你的 gain crossover 如果比 phase crossover 早一点点，早一点点，它事实上就不满足那个震荡的 criteria。但是呢，你会看到一点点震荡，因为它们实在还是很接近，但是呢 ，eventually 它会变成稳定，所以它会震一下，然后再稳定这样子。这个就表示你的 gain crossover 跟 phase crossover 很近，所以我们把它叫做 marginally stable。Okay, marginally stable. It actually, eventually, it will be stable, but marginally. And if we set apart of these two, the gain crossover and the phase crossover frequencies, then you will see the output becomes stable. Okay, so basically this one, the difference between gain crossover and phase crossover is larger than this one. Okay, so you are not going to see this oscillation, but instead you are going to see a stable output. So this is stable. Okay, so here we find that actually the separation of these two frequencies is also very important for your system. And we can define a term called phase margin. Okay, what is phase margin? Phase margin is how far your gain crossover is to, the phase at your gain crossover frequency to minus 180 degrees. Okay, and from this graph, actually, you can see the larger the phase margin, the more stable the negative feedback becomes. Okay, you want a larger phase margin, means that we want these two frequencies to be set apart. Okay, if they are too close, you'll still see some oscillation like this. Okay, but if we can increase the separation of these two frequencies, you are going to see a more stable system. Okay, let's look at this example. So this is omega P1, and this is omega P2. Omega P2 is the gain crossover, and if we correspond this to the phase plot, we see when the gain when it reaches the gain crossover frequency, the phase at the time is minus 135 degrees. Okay, and actually the phase crossover is right, maybe right here somewhere. Okay, so for the phase crossover, the phase will be minus 180 degrees. Okay, so in this case, the phase margin is 45 degrees. Okay, right? The gain crossover, the phase of gain crossover is minus 135 degrees. So the difference between this one and the minus 180 degree is 45 degree. So phase margin of this system is 45 degree. And for well-behaved response, maybe we need more, 60 degree, for example. Okay, so we want to increase the phase margin for your system to stay stable. Okay, and here we can see another, okay. So that's the idea. We want to separate the gain crossover and the phase crossover, okay, so that we can have enough phase margin. Okay. So now I'm going to introduce to you another concept called frequency compensation. Okay, let's look at this figure first. So if in your system the gain crossover is actually later than your phase crossover, like this. Okay, the original design, you have the gain crossover right here, right? But your phase crossover is actually here. So your phase crossover actually happens before the gain crossover. For the original design, your circuit will oscillate. We want to find a way to compensate the circuit, so this frequency response actually shift to here. Okay, if we somehow can shift this response to here, actually the gain crossover frequency is shift from here to here. Okay, if we can shift it, if we can shift the gain crossover frequency from here to here, actually now it happens before the phase crossover. Then the system becomes stable. Okay, so this might be the original design. And if we do some frequency compensation, we can move the frequency response like this. So we will have a new gain crossover frequency to make the system more stable. Okay, then this is the case. So the original design, we have 1 pole, 2 pole, 3 poles. Okay, pole number 1, omega P1. Here is pole number 2, and this is pole number 3. Okay, and you can see for phase equal to minus 180 degree, the frequency here is the phase crossover. Okay, so for the original design, actually, you see the gain crossover is here, right? While the phase crossover is here. So this circuit is not stable because the gain crossover happens actually after the phase crossover. To make it stable, we try to move this omega P1 from here to here. Okay, this is omega P1. We want to shift this pole from here to here. If we can shift it from here to here, the new compensated phase frequency response becomes like this. Okay, and then the first pole, right? And then the second pole, like this. So now the new gain crossover becomes here. Okay, so the gain crossover frequency is shifted from here to here. Okay, so now it's before the phase crossover. Then your circuit will become stable. This is called frequency compensation. The new phase plot will become like this one. Okay? And the phase margin you can get is this. This is the gain crossover. So it's right here. So that is the phase. So this is the phase margin that you have. Okay? So this is the phase margin. So basically, we just want to shift the gain crossover toward the origin from omega P1 to omega P1 plumb. Okay, and let's look at, that's the idea. Okay, let's look at one example. So if we have this circuit, from what we have learned, if we look at the signal path from V in to V out, you see V in will go to here. This is a common source amplifier. And then from here to here, this is a common gate amplifier. And then from here to here, this is another common source amplifier. Forget about this capacitor right here. Okay, this is what we are going to use for compensation. So right now, just forget this capacitor. So as what we learn, actually we will have 3 poles, right? Because we will go from here to here as a common source, and here from here to here, from A to B is a common gate, and from B to VL is another common source. So actually we will have 3, right, poles. 1, 2, 3. We are going to have 3 poles. So this is a 3-pole system. Okay, so for simplicity, we can write down these 3 poles with the 1 over RC observation. So the first one is here. Okay, the capacitor, parasitic capacitor here, we call it CA. Why the impedance look into here is 1 over GM. Okay, so 1 over GM times CA, and at the denominator, so we will have 1 pole here at node A. We'll have another pole here, right? So this is maybe parasitic capacitor is CB, and impedance you will look at is this impedance in parallel with this impedance, right? This impedance is GM2 R2 times R1, and this impedance is GM3 times R3 times R4. So these 2 impedances are in parallel. So you are going to see there's another pole here at node B. Okay, GM2 R2 R1 is this impedance. GM3 R3 R4 is this impedance. So these 2 are in parallel. So 1 over RC, right? That's here. Another one is at CV out. So this impedance is R5. This impedance is R6. So we will have 1 over R5 in parallel with R6 times C out. Okay, so this is a 3-pole system, right? So for this 3-pole system, this will be a very high frequency, right? Because it only has a very small 1 over GM as the resistance. So this will be at a very high frequency. And this will be the dominant frequency because we have a very large resistor right here, right? So this will be the dominant frequency. This will be a frequency at a pole at a very high frequency. This one should be in the middle. So we can make a good assumption, omega PB, this one will be dominant. And the second one will be this omega P out. And the third pole will be omega PA, right? So we can draw something like this. Okay, omega PB, omega P out, omega PA. So 1 goes to 90, minus 180, minus 270. Right? This is what we have. By looking at here, if we want to do the frequency compensation, we can simply add this capacitor at this node, right? Because we want to ship this one, right? If we want to do frequency compensation, we want to ship omega P1 from here to here. Okay? If we ship this omega P1, then we just need to add a capacitor right here, right? How do we do this? Actually, we can add this capacitor. So basically, this will become CB plus see compensation, right? So we just add a compensation capacitor right here. By doing this, actually, we can shift this frequency omega PB from here to here. Okay? And if we can shift it from here to here, actually, we will have a new frequency response like this. Okay, look at the original frequency response. So this is when the system is minus 180 degrees, right? So basically the gain phase crossover is here. So this will be the phase crossover frequency. Okay, so phase crossover frequency is here, gain crossover is here. This system is not stable, right? Because phase crossover is here. But now if we shift omega P1 from here to here, then let's look at it again. The phase crossover frequency is this one, right? Why gain crossover now is happens before the phase crossover. So now actually the system is stable. Okay? So by using one compensation capacitor, we can shift the dominant frequency, and then we can make the whole system stable. 好，所以这里是介绍一个办法啊，就是原本是一个不 stable 的 three-pole system，OK？ 因为它的 gain crossover 事实上出现在 phase crossover 之后，但是呢，我们可以想办法把 dominant frequency 的这个 pole 呢往这个低频移动。好，那我们把它从这个地方往低频移动了以后呢，我们就可以让这个 gain crossover 出现在 phase crossover 之前。好，那它就变成 stable。But there's a price, right? Because the bandwidth is very small now. 对不对？因为频宽现在就非常小了，现在只有这个频宽了，对吧？所以我做了这个 frequency compensation 了以后，我其实会牺牲频宽。好，我会牺牲频宽，应该有发现吧？哈，但是我牺牲了频宽以后呢，记得我可以用 negative feedback， 然后再加大它的频宽，对不对 ？negative feedback 可以让你的频宽变成这个原本的频宽乘上1加 loop gain 嘛，所以我可以再用 negative feedback 把它频宽再加回来，这样子。好，所以我可以用这个做 open loop amplifier， 好，就是 feed forward system 的那个 amplifier。然后呢，我再用 negative feedback 把这个频宽，把这个往这边 shift。OK， 你记得哈 ，low frequency gain 会往下降，但是频宽会加大，这样子。好，所以我就可以把我的频宽加回来，这样子。然后这个电路还是稳定的。好，这个叫 frequency compensation。OK， 然后呢，刚才讲到频宽啊。We can compensate the circuit so that we can have a stable design with the price of a smaller bandwidth. And from our previous discussion, we know that if your bandwidth is smaller, actually the speed of your circuit will degrade. Okay, so we will see some speed degradation of the circuit. OK， 所以你发现其实这个电路设计呢，就是把这边弄好，那边又不好，这边弄好，那边又不好哈，常常会有很多的这个 trade off 这样子。但是 stability 事实上对你的系统是非常重要的，所以没有办法，你只能牺牲哈，因为你不会希望你的做出来的是一个不稳定的系统，所以你只能去牺牲这件事情。好，就是减少频宽，增加稳定性，好，然后呢，它可能电路会慢下来。但是刚才我有讲，我们可以把它放回那个 negative feedback system 里面。那这样子的话呢，我的频宽又会增加，这样子，好。但是呢 ，low frequency gain 又会下来，所以你要一开始把它做高一点。你开始把它做高的话，下来一些也是还是你能接受的，这样子，好。Okay, so this slide actually want to tell you from a designer point of view. OK， 就是我们刚才这边讲是，我给你一个电路，然后给你电路的时候呢，你分析一下你的phase margin 是多少等等。好，比如说 ，for example here, the phase margin is this. Okay, this is your phase crossover. This is your gain crossover, right? So your gain crossover of the compensated system is like this. So if you want to calculate the phase margin, you should do this. So this is the phase gain crossover. You look at here, right? So basically the phase margin is this. Okay, so you can analyze your circuit by doing this, and you can get your phase margin. But from the other side, if you are a designer and you just purposely design your circuit to have certain phase margin, how do you do that? Okay, so this slide show you how to do this. For example, here we have a 1, 2, 3-pole system right here. How do we design how much compensation we want? Okay, so first you want to identify a phase margin. How much phase margin you want to use? Okay, 第一，决定你想要多少 phase margin. Okay, so from this phase plot, once you decide how much phase margin you want, right? This is minus 180 degree, and if you know exactly your phase margin, how much you want your phase margin, you can add this phase margin to here, right? So if you decide how much phase margin you want, actually you can find out this phase, and then you can find out the corresponding frequency, right? So if you find out the corresponding frequency, this frequency will be the gain crossover of your compensated system. So this will be the gain crossover, and you can draw a minus 20 dB per decade slope all the way and hit here. And this would be your dominant frequency, dominant pole of your new circuit. And you just design a capacitor to shift this node, this pole from here to here. Okay, so this is from the designer point of view. 所以刚才前面我们是在讲说，好，那我给你一个电路，你要怎么样去知道你的 compensation 你的 phase margin 啊，好，然后你的phase margin 是多少？好，比如说我给你一个compensation 的电容，你就会知道你的 phase margin。那这里呢，我们在讲说，好，那现在反过来，你是一个设计者，我想要 phase margin 多少？好，所以你是反过来想这件事情。如果你知道一个你想要的 phase margin 的值，好，那你就从负180度加那个值回来嘛。加那个值回来呢，你往这边对，就会对到一个频率。好，这个频率呢，事实上就会对上来，就是你的 gain crossover。好，所以你 gain crossover 的 frequency 必须发生在这里，你的 phase margin 才会是这样。那从这个 gain crossover 的频率呢，你再画一个负20 dB per decade 的线推回去，撞到这个 low frequency gain 的这个 frequency 呢，就是你的 dominant pole 的 frequency。好，所以你就是把你的 dominant pole 从这里 shift 到这边来。那其实你就可以算，好，以刚才那张图，就是那个 compensation capacitor 要放多大，这样就可以算出来。OK， 好 ，so actually you can design your circuit to have a certain phase margin that you want. Okay? And by looking at here, actually, you might wonder that, well, to shift from here to here actually looks like a big shift. So the value of the capacitor might be very large. 好，就从这边 shift 过来，感觉起来那个电容好像很大这样子。Yeah, sometimes it's very large. So can we use a small capacitor but actually effectively, the capacitance is really large. Okay, how do you make a large capacitance with a small capacitor? 我们有没有可能用一个小电容，但是可以有大效应这样子？就是你电容值当然不大，但是呢，等效电容值很大。我们以前学过这个概念，那个时候的概念不是个好，我们觉得这不是个好东西，就叫做 Miller effect， 对不对 ？Miller effect 可以让一个小电容，但是呢，效应很大这样子。Okay, so actually we can do this with a Miller compensation. Okay, so this is exactly the same circuit. But instead of connecting your compensation capacitor right here, okay, let's make a comparison. See, the capacitor was here, right? Now we connect this capacitor from here between this and this. 其实只有一个地方不同，就是这里我们不接地了，咱们把这里接到这边来。好，就是这个 compensation capacitor 这里不接地，我们把从这里接到这边来。That's the only difference. Okay, what's going to happen? Well, this capacitor now becomes a floating capacitor, right? And the input is here, which is at a gate of the common source amplifier, and the output is at a drain of the common source amplifier. Okay, so this is going to give you an equivalent capacitor, which capacitance is this, right? 1 plus AV. What is AV? GM5 times R5 in parallel with R6. Okay, so we actually can use a very small capacitor, but we can have an equivalent large capacitor to do the compensation. Okay, so we can do this to save chip area by utilizing Miller multiplication of a smaller capacitor, and we can have an equivalent effect. 好，所以呢，事实上，我们如果这么做的话，我们就可以用一个小电容，好，然后产生够大的等效电容。那这个事实上是一个 common practice， 就是你如果去看这个 OP 的设计呢，这个电容放在这边是标准的做法，好，就是用这个 compensation capacitor 放在这边和这边之间，好，那前面可能是一个 differential pair， 然后但是后面这一级呢，它就会放这个东西，那这个就是作为 compensation 之用的，好，如果你看到电路的设计的话 ，OK。好，所以呢，到这个地方，我们基本上把 feedback 做一个结束。好，那我们讲到这个 feedback 的时候呢，我们从最前面我们讲，我们要做一个 negative feedback system。好，那 negative feedback system 呢，事实上就用了我们前面所教的这个 amplifier， 然后这个 amplifier 呢放在这个 negative feedback system 里面了以后呢，有非常多的好处，好，包括了它的 gain 不会那么的 sensitive to variation。包括了 bandwidth 会变大 ，input impedance、output impedance 也会变好，整个电路变成更 linear 这样子。好，那我们也讲了各种不同的这种 input 跟 output 之间，好是 current 还是 voltage，current 还是 voltage 之间的关系。好，那最后呢，我们就讲到 feedback 没做好，它会震荡。好，所以也不是做了就 OK 了 ，feedback 没做好会震荡，所以我们需要注意这个，当我们的 system 里面有好几个 pole 的时候呢，要注意让它不要震荡。好，我们做一些 compensation 的事情。好，那这个呢，事实上是其实讲完了这个东西。然后呢，好像我们忘记把新的东西啊，你已经传上什么 EE class 了吗？哦，我们之前忘记把这个新的东西传上 EE class， 然后我跟大家讲，没关系，这里其实好像也只剩下10分钟了，还讲吗？都可以。对啊，以我的个性，肯定是不讲了。我看一下，好了，我们只讲最有趣的地方，然后就不讲了。好，等一下。 好，先给大家看，好，来到这边哈。好，先给大家看这个，这个是我们这学期的 schedule， 给大家再看一下，看一眼啊，看一眼，我已经完全的追到了。我们已经上完这个了，这样子，12月7号这样子，然后今天是12月8号，然后12月8号这个9.1其实很简单，几句话就讲完了，尤其是我讲中文的话，应该一下就讲完了。好，讲英文可能还会不小心讲太久这样子。好，所以我们基本上已经追到进度了。然后下礼拜我有跟大家讲，我下礼拜临时被叫去出国，对不对？好，所以我们下礼拜不上课，不要跑来这样子。好，然后那个。但是回来我们一定会来得及上完哈，然后呢，那个上次问大家哈，这个吉隆坡跟新加坡要买什么东西回来，没有人回我啊，所以这个如果有想到有什么好东西的话，记得提醒我一下，我可以把它带回来，应该比这边温暖多了，这边最近有点冷这样。好，所以大概是这样。Homework 6昨天出了吗？出了对不对？哦 ，OK 好。Homework 6跟这边没有关系，对不对？对 ，Homework 6跟大家没有，跟这个我来不及上的课没有关系啊，所以我很安心，没事。好，然后呢，好，我讲几句好了。这个9.1其实非常的简单。OK，Let me say a few words. OK，Actually, the next topic， 你们，我不知道你们有没有拿到投影片，现在看到了还是？好，因为我们忘记把它放上去了，没关系，前面非常简单哈。Actually, this topic we want to talk about operational amplifiers. OK， 就是我们想要讲这个 operational amplifier 之前是一个三角形，我们想讲各种各样的放大器。好 ，and we are going to use another textbook called Design of Analog CMOS ICs. OK。And we will use the content in Chapter 9 of this textbook. So this will be another textbook. Okay, these are from Razavi's, I think, is Fundamental Microelectronics. This will be another textbook. And this is a very important moment. 那个鸿儒可能要拿起你的手机，好，帮忙录个影这样子。OK 吗？不是录我，你要录大家。等一下，好，跟大家说一下哈，因为呢，后面这一次这个课呢，和这个应该是说这个 topic 跟这个 topic 呢，我懒得做投影片，所以呢，我们用了谢老师的投影片。好，那我们要非常感谢谢老师，大家来拍个手啊。好，可以了。好，这个要传给他。OK， 好，谢谢。好，这个是非常重要的环节啊。好，所以呢，接下来呢，大家可能会发现这个投影片的 style 跟前面都不太一样哈。大家可以比较一下哈。那这个投影片，如果大家觉得看不太懂不是我做的啊。OK， 好，这个 Chapter 9 Operational Amplifiers。OK，so the outline。General consideration is 9.1. This is what we are going to quickly go over. 我们其实很快就讲完了这个东西哈。那事实上呢，它就是要讲 OP 很有用。好，然后呢，there are some ideal characteristic of the op-amp. First, you need a very high voltage gain. By now you understand, right? Because we want a very high open loop gain in the feedback system. So we want this, the gain of the OP to be very high. And also high input impedance, because for the voltage amplifier, we want the input impedance to be as high as possible. We want the output impedance to be as low as possible. Okay, so by now you understand all of this. Actually, there are some other considerations such as speed. Okay, we talk about speed, right? The speed, if your speed is not enough, your OP is going to slew. We talk about slew rate, right? That has something to do with the speed. And another thing we didn't talk discuss is the output voltage swing. We are going to talk about this. How much you can swing your output, how low can your output voltage go, and how high can your output voltage go. Okay, that's the output voltage swings. And power dissipation, how much power consumption you have in your OP. Okay, and this circuit is not important. Okay, so basically these are the general considerations of the operational amplifier. Okay, and remember this, our old friend, non-inverting amplifier, right? We can use this operational amplifier to insert it into a feedback loop. Okay, so remember this. We can derive VR over Vin equal to this. 我们之前都导过，对不对 ？Non-inverting amplifier， 事实上你会得到 A1 divided by 1 plus KA1， 对不对？好，就是这个 closed loop system。你把它重新写一下，就会变成这样。OK， 好，那如果呢，你的 A1 非常非常大，这个东西就会近似于它，但是会有一个这个 gain error， 记得吗？我们前面讲过，它会有一个 gain error 啊。然后你的 gain error 呢，事实上，this is the gain error. Gain error has something to do with the closed loop gain. Okay, and also A1. So if you want your gain error to be very small, then you will need to have a very large open loop gain. For example, here, if we want this, if we want 1 plus R1 over R2 equal to 10, this is 10. So if you want your gain error to be 1%, this is 10, this should be 1,000. So this is just to tell you, 我们就是带几个数字进去, this is just to tell you that your open loop gain should be very, very high for your gain error to be small. Okay? And basically, if you just use a common source amplifier like this, it's not very easy. Okay? So for a gain stage, if you just use a common source amplifier, it's very difficult to guarantee the error. Okay, and there are variations for the mobility and T oxide and everything. Okay, and you know that the gain of this one will be minus GM1 times RD. Right? So basically, the gain of this one will depend on the value of RD, which could be 20% error. 好，其实这一页很简单，这一页只要告诉你2个重点。第一个重点就是你只要把你的 amplifier 放在 closed loop system 里面呢，你事实上是可以有一个比较稳定的 gain。但是你的 gain error 要小呢，你也把 open loop gain 做得很大。这是第一个重点。好，那第二个重点呢，只是告诉你 common source amplifier 它是一个 gain。但是这个 gain 的 error 会很大，这样子，所以你会需要做一些 OP 的design，然后因为这个投影片是在讲 OP 的，好 ，Then we'll quickly look at some properties of the OP. The first one is the bandwidth. OK， 所以呢，对 OP 来讲，第一 bandwidth 是很重要的，第二呢 large signal behavior 也是重要的，好 ，large signal behavior 就是当你的input 如果是大的，就是不是很小，是比较大一点的时候呢，你会怎么跑？哈，这个我们后面会看到。然后呢 ，output swing 也是一个重要的事情，我们等一下回来看一下下。然后再来一个是 linearity 就是在讲说你的这个线性度怎么样？好，就是我的 input 是1，然后如果我的 gain 是10。我 input 是2，他要给我20；我 input 是3，他给我30，这个叫线性。好，那再来呢就是 noise， 好，可能会需要注意一点 noise 的问题。那就没有了，9.1就是这么多这样子。好，那等一下我们回来讲一下这个东西。好 ，output swing， because we didn't really talk about output swing before, so the last thing I'm going to tell you today is the output swing. Okay. So for something like this, see, this would be a very simple amplifier that we know before, right? For example, this is Vin plus, and this is Vin minus, and this would be V out. Okay? So for this circuit to work, okay, and for it to provide gain, actually, there has been one assumption. All of them are in saturation, right? 我们之前讲到这个 OP 的时候，我们有一个假设，所有东西都在 saturation 里面，包括它，对不对？所有的都在 saturation 里面。For a transistor to be in saturation, this is gate, source, and drain, and we have to satisfy VDS larger than VGS minus VTH, right? So basically, if we want all the transistors to be in saturation, let's say this is M1, M2, M3, M4, and this is MB, okay? So how high can Vout go? 这个 Vout 究竟可以高到什么地方？它可以 Vout 可以往上，但是它必须要让 M4 留在 saturation， 对不对 ？M4 必须在 saturation。好 ，So there's a minimum requirement of M4, which VDS of M4 need to be larger than VGS 4 minus VTH 4， 对不对？所以呢 ，the maximum of Vout is VDD minus VDS 4， 是不是这样？所以，因为你每一个你如果所有东西都要那个 gain 都要在那个 linear region 里面，他们所有都要在 saturation 嘛，他们所有都要在 saturation， 这个 VDS 就必须够大，它才会让这个 M4 呢能够在 M4 的 saturation region 里面，对不对？好，所以呢有一个最小的 M4 的 VDS， 你的 Vout 呢只能往上到某个地方，你还得满足它。这个就是你非要的上限，好，这是你非要的上限。非要的下限在哪里呢？你看这个 MB， 如果这里有个 VB 的话，这一点我如果叫它 VX， 好，那 VX 就必须要大于 VB 减 VTH， 对不对？因为这一点它要满足它的 saturation，OK？ 那这一点呢，又要满足它在 saturation， 对吧？所以呢，你的 Vout， 好 ，Vout 呢，Vout 减 VX， 就是这个 VDS， 必须要大于 Vin minus 减 VX 减 VTH2。对吧 ？OK， 所以呢，这个消掉了 ，Vout 要大于 Vin minus 减 VTH2， 对不对？嘿，但是呢，又不只是这个，为什么呢？你看，这里有一个 VB、MB， 好，然后呢，把这讲完就下课了哈。这边要留个 IB， 对不对？这边要留个 IB， 这里留个 IB 呢，在这个 DC bias 的时候，是不是要让这边留2/2 IB， 然后这里也要留2/2 IB， 对不对？所以呢，这个地方的 VGS 必须要满足这个 transistor 可以留2/2 IB，OK？但是呢，这个 Vx 又有一个最低的嘛，对不对 ？Vx 有一个最低的值，让这个东西在 saturation。OK， 所以 Vx 有个最小值。 Vx 有一个最小值呢，这个 Vx 就会使得这个 Vin 也有一个最小值，对吧？好，因为这个 Vx 有个最小值 ，Vin minus 又要满足它要留2/IB， 所以 Vin 有个最小值 ，Vin 有个最小值，那 Vout 是不是又有一个最小值 ？OK， 好，所以它 Vout 往上只能到某个地方，往下又只能到某个地方，这个就叫做 output swing。好 ，output swing 就是你的 Vout 到底往上可以到哪里，往下可以到哪里，这样子。好，那这个 amplifier 的 output swing 事实上也是一件重要的事情。有一些系统它会希望你的 OP 有很大的 output swing， 好，否则你放大了半天，它只能在小小的范围里面工作，好像就有点没有用这样子。好，那所以有一种方法呢，它叫做 fully differential。fully differential 的意思呢，就是我不要用 single-ended， 我这样看 ，OK， 我的 input 呢是一个 differential， 我的 output 呢也是一个 differential。我 output 如果是 differential 呢，我就可以有2倍的 swing， 因为一上一下这样子，它就变成2倍的 swing 这样子。好，所以我们可以用这种方法来增加你的 output swing， 这样子。OK， 好，我们等我国外回来，我们再继续讲这个东西哈。反正第9章呢，就是要跟大家讲 OP 的各种设计啦，就是有各种各样 OP 的设计哈。那这些事实上都是我们想考虑的，它的 bandwidth， 它的 large signal behavior， 它的 output swing， 它的线性度，还有它的 noise。noise 我们可能不会考虑到这样子，好，不会谈到。还有一些 supply rejection。noise 跟 supply rejection 我们可能不一定会讲到很多哈，如果有机会我们就谈到这样子，大概就是这样，好不好？那我们今天就到这边，所以我们的 homework 是延到了礼拜天，好，我们 homework 是延到了礼拜天，所以大家 enjoy 一下这个写功课，好，那就这样，那个想到那个东南亚有什么好的伴手礼，告诉我一下。好，我们就上到这里。